Hi there. What is a derivative? Well, hopefully after this video, you will have complete understanding of what a derivative actually is, and hopefully you will see that it's actually a pretty easy concept when it's boiled down to its basics. So here we go. What I have here is a function, and it's a quadratic function, and you might recognize it from a pre-calculus class. This actually turns out to be a position function. It describes the height of an object that starts out with an initial height of 10 feet, with an initial velocity of 100 feet per second, and then this minus 16 right here is our basically our gravitational effect. This is going to be gravity acting on our constant. I'm not going to derive this right now. It could be found in any pre-calculus book or physics book. Okay, so here we go. If you look down here to the y-intercept, you'll notice that it starts off at 10. In fact, if I move this yellow ball to 0, this represents time equals 0, and you can see that when time is 0, that the height of my initial object is 10. Now remember, let's say I'm standing on a basketball hoop and I throw an object up as hard as I can. It just goes straight up, and then it's going to peak out, and then it's going to fall back down. That is what this curve represents. It represents the height of an object thrown straight up, and as it goes up, it charts its height, and then it peaks out, and this represents it falling back down to the ground. Okay, so you can see I've attached these yellow balls to some other balls on the parabola there, so I can really figure out how high is this object at any given moment in time. If I move this to 2, okay, here we go. I just moved this to 2 seconds. 2 seconds into the flight, the ball or whatever I'm throwing up is 145 feet up in the air. I can move this other ball to 1 if I want, and this tells me that, this tells me at 1 second the ball is 93.84 feet high. Okay, well let me ask you this question then. What if I asked you what is the average velocity of the ball? The average velocity of the ball from the time it started at time equals 0 to 3 seconds. Over the first 3 seconds of its journey, how fast on average was it traveling? Well, how would we do that? We need a couple of things to calculate the average speed of any object. Okay, we would need a distance traveled, and we would need a time that it took to travel that distance. This is what average velocity is. It's the change in distance divided by the change in time. Real quickly, if you traveled 300 miles and it took you 5 hours to do that, okay, so the net change in your distance is 300, and the net change in your time is 5 hours. Well, 300 divided by 5 is 60 miles per hour. Okay, and everybody recognizes this as a rate. Okay, if you're driving in a car, you might even say that that's your speed. Okay, 60 miles per hour would be your average velocity or your average rate of change. All right, so with this problem, I want to know what's the average rate of change over the first 3 seconds of this object's flight. Well, how far did it travel? If you look carefully, I've constructed this triangle here, and this leg right here represents the distance traveled from the initial position to the final position. Okay, the final position can be read off here. It's 166. The initial position is right here, which is 10. So 166 minus 10 is 156 feet traveled over the course of 3 seconds. So if I'm writing this down, I would write 166. This is my final distance minus my initial distance, and I'm going to divide that by 3 minus 0. In other words, this represents my time that it took me to go this distance. Okay, 166 divided by 3 is equal to 55 point, what would that be? 55 point, let me calculate this real quick, divided by 3, 55.3, 55 and a third. Okay, we'll just write 0.3 repeating, and this is feet per second. Okay, that would be the average rate of change for my object over the first 3 seconds. Okay, well, let's change the problem then. Let's change it to what is the average rate of change of this object in between 1 second and 3 seconds. Well, once again, I can calculate the distance traveled, and the distance traveled here is going to be from 93.84 to 166. If I subtract those two, that's going to give me the distance traveled divided by the time it took it to go there. Okay, so I've actually I've done this already dynamically, and you can see that 166 minus 93.84 is 72.6. Okay, the time it took it to do that, in other words, what is the time from here to here? Well, that's simply going to be my final time, which is x plus h, minus my initial time, which is 1, and that gives me a time of 2 seconds. So I went 72.16 feet, and it took me 2 seconds to do that. All right, well, what is that calculation? Let's just go grab these. 72 divided by 2, and that equals 36.04. Well, for those of you who are already familiar with a derivative and the idea of a derivative, this may start to look familiar. In fact, if you look carefully at this denominator, some of you might recognize that you can actually simplify this, and this simply simplifies to h. Okay, more on that in a minute. Okay, so the average rate of change then from 1 to 3 seconds would be 36.04 feet. Now, let's change the question yet again. Let's say that we want to creep in a little bit closer, and now if I want the average rate of change in this time frame, what would the average rate of change be? Well, my distance right here is 52.49, and my time frame is right around 1 second. So let me try to get that a little bit closer to 2. There we go. And so you can see that your average rate of change is right around 52. Now it should be 52.24. I suspect there's some rounding error going on in here. That's why you see this different. Obviously 52.24 divided by 1 is not 52, it's 52.24. Okay, well, what would happen if we ask this question? What is the velocity of this object, not over the course of any given time, but at a very specific time? Up until this point, all we've been doing is calculating the average rate of change by calculating the slope of this line. Well, what if we let this time get infinitely close to the time we're interested in? What if we were interested when time equals 1? How fast is this object traveling when time equals 1? Well, you'll notice that your secant line is really now a tangent line. Okay, but all these calculations still mean the same thing. This represents the distance traveled, and this represents the time it took it to do that. So you can see that 67.86 feet per second is how fast this object is moving at time equals 1. It's an instantaneous velocity. Now, I had to keep this back from 1 exactly, because if I let it go to 1, the program doesn't like that too much, and you can see that your tangent line disappears. You get some undefined stuff over there. That's because we're dividing by 0, and the program doesn't like that. Okay, so we let this close in as close to 1 as we can get it, and if we get it close enough, we can estimate what that instantaneous velocity at time equals 1 actually is. Okay, so really what you just observed was a derivative. Let's write it out. What we had was we had a final distance, and that final distance was f of x plus h. And we subtracted from it an initial distance, the distance that we started out at, and that was f of x. For those of you who don't know where that came from, okay, it simply came from this. This height is f of x plus h, because that's where this point is. And this height right here is simply f of x. Here's f of x in red. Here's f of x plus h in green. So if I subtract the two, I get a total distance. Divided by what? Divided by a total time. Now what is my total time? My total time is represented by this distance right here. And we already saw up in this calculation that if you subtract x plus h and x, we just get h. Okay, look right here, look at the algebra. Your x's go away and you're left with just h. Okay, so what I'm interested in is when this h, when this value of h gets really close to 0. Okay, so instead of writing x plus h minus x, I'm just going to write h. Okay, now what did we do? We said let h get infinitely close to 0. So we let h get extraordinarily close to 0, and we see what happens to this quotient. This right here is equal to the derivative. This is the derivative. What's a derivative? It's a rate of change. In our example, it's an instantaneous rate of change of an object that's being thrown up into the air. Okay, so this is your derivative. Now getting back to the picture, let's go to an intuitive part of the graph, which is up at the top. I just want you to think about how fast the object is traveling when it's at the peak of its journey. Okay, think about it. You throw an object straight up, it stops, it changes directions, and comes back down. So what is the slope of this horizontal tangent line? Well, the slope of that horizontal tangent line is, if it's truly horizontal, looks like it's not exactly horizontal here, but if it's truly horizontal and I'm truly at the peak, the slope of that will be 0. Okay, so that is a visual look at what a derivative is. We looked at it in terms of average velocity first, and we looked to see what would happen if we took that idea of average velocity and entertained the idea of instantaneous velocity. I hope that helps. In the following videos, we will look at some more specific examples. Thanks for watching.